Good morning, Jenkins world. My name is Andre Falco. I want to tell you today about my journey in automating security updates to Docker images. I've been at Lyft for just over 1 month. Prior to that, I was at Salesforce for 9 years. The reason I'm representing Lyft today is because the strategy that Lyft took to solve the problem was almost exactly the same strategy that we developed at Salesforce. I'm going to start off by explaining what the problem is that we're trying to solve. I'll go over the solution that we came up with. I'll have a live demo showing some open source tooling and action that you can apply yourselves. I'll then go over challenges that you'll face even after deploying the solution in the live demo. And finally, I'll conclude with takeaways and acknowledgments. Our Docker images consist of a large number of packages. These packages you can kind of think of them as your tool chain. That tool chain resides in your base OS, and things like Java or Python or Node can't work without that tool chain. Because there are several hundred packages that make up that tool chain and your language images, your application images, by conjunction, become vulnerable over time if you don't patch them. What happens is, over time, security researchers find vulnerabilities in your toolchain packages as well as your language packages. They find those vulnerabilities and they responsibly disclose those to the package maintainers. Those maintainers get a chance to create a code change, and if the vulnerability is critical enough, they work with various Linux distributions to package them up and get them ready to be consumed by people like us who are deploying these tool chains and depending on them for our applications. Once distributions are ready to go and the code patch is in, a public disclosure is made, and we're all in a race against time to get our production systems patched. One of the strong points of Docker images is that they're immutable objects. What you are building and testing in your development environments is going to be exactly the same thing in your production environments. However, the problem with that is that immutability property means that if there is a vulnerability in any dependency that you depend on, you have to rebuild the Docker images that contribute the layers in your dependency tree. You have to do these rebuilds in a particular order and at a particular time, and if you do them manually, you're going to make mistakes. For example, if there's a vulnerability in your base OS image, and you simply rebuild your application image is going to continue being vulnerable because you haven't rebuilt both the base OS image, the Java base image that depends on it, and then your application image. Order matters. If you make any mistakes in your security patching process, you're going to set yourself back. If we push a security update that breaks your application, which happens from time to time, you're going to suffer a rollback in production, which forces you to go back to square one. And during that whole time, your production systems are left vulnerable. Now, we can naively maybe say, let's rebuild all of our Docker images continuously. Eventually, all the vulnerabilities will go away. However, if you have hundreds of images or thousands of images, you're going to spend a lot of money on compute to maintain your CI environments. At Salesforce, every time that we would have a vulnerability in the base OS, it would consume all of the CI resources that we would have. For Lyft, which likes to scale things up and scale things down based on need, we'd have to keep things scaled to the max if we were to follow that naive strategy. So what can we do? Since we're at Jenkins World, I think a lot of you are probably familiar with test and release pipelines. We basically make all of our Docker images be built through a test and release pipeline. You build and test your image. You integration test it. And then you publish it to your registry. After you publish it, the solution is to create pull requests to all child images that depend on that specific image. The pull request pipeline for that child image then kicks off. If you have testing enabled, especially integration testing, you'll have hopefully a green pull request. If it's green, you merge it, and you go through your master pipeline, which again, you test it, you build it, you integration test it, you publish it, and again, generate pull requests to any child images of that image. So now you have a recursive cascade of pull requests that reverberate through all of your layers of your dependent Docker images. And if that pull request doesn't go green, then that signals to your developers or your service owner that, hey, you need to prioritize fixing this because security updates are blocked for whatever reason. While I was at Salesforce, we open sourced a tool called Docker File Image Update. It's a command line tool that can be invoked in Jenkins. In fact, it was designed to be invoked in Jenkins. The tool has a number of subcommands. The main one that generates these pull requests is the parent subcommand. The first parameter that you give it is the parent image. The parent image is the name of the image that you're building, so you hopefully know that because you've just published it in your test and release pipeline. The second parameter is the intended version. So you've just published a version, you pull that out, plop that into the command line. And the third parameter is a persistence repository where we keep the image to version mapping. I'll get into that in a little bit. Here's an example of the command without any of the funny brackets and stuff. Here we're saying send pull requests to all images that depend on CentOS 7 JDK and update them to version 10 and persist that mapping in image in a repo called image tag store. The image tag store, as I said, is just a mapping of image name to version. The reason we persisted in a Git repo is to make the tool easier to use. You don't have to set up a database. Just use a Git repo because it has to have access to Git anyway, or GitHub specifically. The repository is read by the all subcommand. The all subcommand goes through the list of image to version maps and sends pull requests to any repositories that have gotten out of your intended state. Now, why would your repositories ever get out of intended state? When you're dealing with pull request flow, there's a lot of edge conditions that come into play. For example, a lazy developer, such as myself, might create a new image. I'm lazy, so I'm not going to be bothered to look up the image version that was published last. So I'm just going to depend on a copy-pasted version from another repo. And then I submit that, I launch my first application, and boom, I'm vulnerable day one. The all subcommand will correct repositories like that by sending pull requests to them. Another edge condition that you'll face is if you give your developers a lot of control, they might have control over merging into master directly. So they might be working off an old branch, and they force push it into master for whatever reason. This will, again, correct that kind of edge condition. If you have a lot of images, you might want to run this at a slower time cadence. If you have a lot of, or a small number of images, you can run it at a quicker cadence. Here's what one of the pull requests look like. Pretty simple. We're bumping Alpine Java image from version 7 to 11 in this example. So let's pray to the demo gods that this live demo will succeed. What I will show you is a state where we have a number of images that depend on the Alpine base image. There's a number of applications that depend on their respective language images. And our starting point is that they're all vulnerable. If this demo works, then all of the vulnerabilities will get fixed. So this is the Alpine image, our base image. It has two vulnerabilities in this vulnerability, as reported by this vulnerability scanner. As you can see, it's an old version of BusyBox. That's the culprit. So really only one package needs to be resolved in this image or fixed. If you look at Alpine Java, just as I was describing earlier, it's going to be vulnerable to the same thing because it depends on that image. And the vulnerability is exactly the same. If we go to Hello World app, which is a Java app, it's vulnerable to the same exact thing because it depends on Alpine Java. And then finally, if we look at one of the Python apps, again, same story. So let's fix this vulnerability. What I've done from demo purposes is I pulled off an old image from an old demo that I ran of that Alpine base image. I'm going to comment that out, and I'm going to have it use from scratch in a bootstrap tar that has the contents of our base OS. So let me commit that and let that run. So here's our master pipeline. Let's make sure that that got kicked off. Yes, it did. So let me show you. So you can see that I have a pipeline here. I'll show you what that pipeline looks like. Build and test bootstraps our base OS. So we have full control over the build process as well as the versioning process. We're using Alpine chroot tooling for that. The publish stage only runs on the master pipeline. That's the stage that publishes to a Docker registry, in this case, my namespace in the public registry. And then in order to show vulnerability scanning in action, we publish it to GCP registry. And then most crucially, update Docker images is another stage. Again, it's designed to only run on master after you publish. It takes the following parameters. First is the GitHub API URL. If you're using GitHub Enterprise, this will work with that. There's an API token that you need to get it to work. This is the Git tag store that I was mentioning earlier. We've packaged it up as a Docker image that you can use without having to install anything except Docker in your CI/CD pipelines. Here I'm having it run against my own org. We don't want this demo running against all of GitHub. That would be pretty interesting. Here's that parent subcommand, the image name, And for versioning, we're just doing versioning by build numbers in Jenkins. So let's take a look if it finished. Yes, it did. You can see that there's some command line, or sorry, some logging that it does in case you need to troubleshoot anything. And now we have a pull request to Alpine Java. And we also have a pull request to Alpine Python. Let's take a look and see how those are progressing. It looks like Alpine Python might have finished. Oh, sorry, that was the master branch. Oh, look, it went green. So let's take a look. It is green. If we look at the pull request, again, it's just a simple version bump. We'll merge this. Alpine Java, let's see if it went green. Yes, it did. Merge that. So now the master should kick off for Alpine Java. Yep, there it goes. Let's take a quick look at Alpine Python. That's going to finish pretty quickly. If we look at the Jenkins file for Alpine Python, it has pretty much the same thing. The only thing that changed with our invocation of Docker file image update is the image name. As you can imagine, this would be really easy, and in fact, I encourage you to do this. You can use a Jenkins file shared library so that you don't have to rewrite and recreate this command line for all of your Jenkins files. So that one is almost, oh, there it goes. It finished running update Docker file image update. So now there's a pull request to Python test app. That got kicked off. That's in progress. Python 3 test app. So now we've cascaded up to our application layers. This one, so this is the hello world app that depends on Java. Java's a little slower than Python for building. The one thing that it's slower at Python at. Let's take a look at the pull requests for Python. So, we have a red pull request. Our Python 2 test app failed in pull request. Let's take a look and see what went wrong here. So it's pull request number 32. It failed in our build and test phase. So what happened here? We have a syntax error. If we look at Alpine Python, it's a Python 3 image. I purposely made this a Python 3 only image for this demo. Why did I do that? Because this is a Python 2 test app. At one point, the image that it depended on supported both Python 2 and Python 3, and I broke it. What's good is we've now prevented a production rollback for this Python 2 test app by employing our pull request flow. At this point, Java has finished, so we have a new version of Hello World app to update. So let's merge that. Let's also merge Python 3 test app. Let's make sure that they got kicked off. Yep, the Java test app is kicked off. And Python 3 test app is almost done running. Here's what the Docker tag store looks like. You can see the previous versions in the map over there. If we refresh the page, you see that they get bumped up, so that worked. And now let's take a look at what our state is in GCP, in the GCP registry. Whoops. So Alpine now is fixed. Let's see if Alpine Java is also fixed. Yes, it is. Alpine Python, also fixed. Hello World app just finished its run, so it doesn't have the vulnerability anymore. Python 2 test app is going to keep being vulnerable until we get that pull request going green, or force merge and cause another failure. And then finally, Python 3 test app is no longer vulnerable as well. So we got really lucky. Nothing went wrong in the demo. All of our vulnerabilities are now fixed. So there are a number of headwinds that made this demo possible. One thing that I mentioned already is that we had control over the whole build process. We were building from scratch. If you are in an environment where your security requirements are to have air gaps, you might not be able to pull public images from the public Docker registries. And your only recourse is to build things from scratch and bootstrap from sources that are internal. That takes a lot of work and effort. The other thing that controlling the build allows us to do is control image versioning. Controlling the image versions and not depending on descriptive versions such as latest, or in this example, CentOS 6 or CentOS 7, is powerful because any code changes can get reflected via pull requests, specifically version bumps. A developer or service owner that's receiving these pull requests is able to read that and immediately grok that, oh, there's a new version, I must update. If you don't control image versioning, if you're depending on public images, which is something that you should probably do unless you want to reinvent the wheel, is the vendors who produce the Docker images, they're going to have versioning schemes that are probably different from yours. Additionally, they're not going to send you notifications. They're not going to send you pull requests when they have a new version updated. They're not going to send you notifications either, especially if your repositories are private. So what can you do? At Lyft, we use intermediate repositories. These intermediate repositories go through the same test and release pipelines everything else goes through, but they pull from public repositories and remap to our own versioning scheme and upload to our internal registry. Only a few of these intermediate repositories are allowed to pull from public sources. Everything else has to pull from your internal registries. Once you've remapped from public to your private base OS images and gotten control over versioning, you still have the problem where the public images have a different version, usually have a descriptive versioning scheme. Like in the previous example, we're using Ubuntu latest. You don't know when exactly latest is changing out from under you. When you're pulling images from an image vendor, you need to research and make sure that they practice security updates, and usually they do that with a particular time cadence. If you schedule things to their time cadence, you'll pick up their security updates. And then you can kick off the master pipeline of your intermediate repositories. An optimization that you can do, which I haven't seen implemented yet, but wish we would do this, is having tooling that tracks when the digests of the public images change for descriptive tags, and when they do, that automatically triggers the pipelines for the intermediate repositories. Another problem that you'll likely face when you have hundreds or thousands of images is service owners don't merge the pull requests on a timely manner. If those pull requests are not merged, then all of our efforts have been for naught. What we do at Lyft, which I really like, is we've set a contract with service owners where these pull requests will be force merged within a certain time period. Further to that, you'll have a merge happen even if it's red. What this does is it bubbles up the priority of these updates to developers. They know that if they ignore these pull requests, especially if they're red, they're going to be blocked from releasing. They're going to have to slow down their releases in order to fix master. So generally what I've seen so far is developers are on top and gung-ho about fixing these merges. If you're just now waking up from your long nap after listening to my monotone voice, here are the 3 cheat sheet items to take away. The first, it's important to automate routine security patching. If you leave it up to manual processes, you're going to make mistakes. And any mistakes that you make set you back and delay the time with which your systems lose vulnerabilities or become patched. The next takeaway is when automating routine security patching, keep testing within that cycle. It's important for developers to get the feedback when things are about to break. You want to avoid rollbacks because they're costly. And finally, if you're going to use public images, vet the vendors and take extra steps with getting those images into your private repositories. Here's another link to Docker file image update. Users and contributors are more than welcome to check it out, contribute, use it. If you know of tooling that does this better, please let us know. We're always looking for ways to improve. Some of the things that are on the roadmap item that are wish list items are auto-merge support, supporting declarative formats for Docker images other than Docker files would be nice. For example, some developers like to declare their Docker images with Maven. It would be really cool to extend this tooling and this pull request flow to production deployments. Why not update Docker Compose YAMLs or Kubernetes pod YAMLs in addition to your Docker files? More generally, I'd like to see the industry move to sending pull requests for updates to other packaging types. What if you got pull requests to your Maven POMs or your Python pip packages, RPMs, DPKGs, everything? And finally, I mentioned this earlier, it would be nice to have something that auto-detects changes to descriptive tags such as latest. I want to thank Minho Park, our intern at Salesforce, who wrote the initial version of Docker file image update. Justin Nelson and Janesh from Salesforce, who helped get Docker file image update into production at Salesforce. And finally, the Lyft productivity team, Ryan, Anish, and Brian, who've built almost a parallel universe of tooling at Lyft to take on the same strategy and improve it. Feel free to reach out to me at any time, and I'd love to open up the podium to any questions.
Yes, so what if you have a mono repo with different Docker files? Does the pull request process workflow still can work, or do you end up with potential merge conflicts if things items can't be merged?
So the question is, if you have a mono repo that has a bunch of Docker image definition or Docker files, will the tool work for that, and how will merge conflicts work in that? So actually, Janesh from Salesforce recently submitted a feature set that allows you to have multiple Docker files in a repo, so you'll get pull requests to those. If you have merge requests, or sorry, merge conflicts, then yeah, either they'll probably become red pull requests, so it'll kind of bubble up for you to have to fix that in some way, shape, or form.
And so in that case, the Jenkins job will fail.
Yeah.
Okay. Thank you.
Back there.
Does it support either Bitbucket or GitLab or only GitHub?
The question is, does it only support GitHub? Does it also support Bitbucket or GitLabs? Right now, it only supports GitHub, but that would be a great wish list item. Yep.
So I think I missed that part where when a pull request for the Alpine Docker file is merged, what thing automatically triggered creating pull requests for Alpine Java and Alpine Python?
So the question is, when the pull request was merged for Alpine, what triggered the pull request creation? So that was the Dockerfile image update tool.
And that was run in the Jenkins file? Or
Yeah, so it was run in the Jenkins file. I can show that again real quick. So in the Jenkins file, this was the step that was run. And yeah, like I was suggesting earlier, if it's a shared library, then it makes it easier to roll it out to your Jenkins files. Any more? Oh, back there.
The column for vulnerabilities in the Google screen, is that I don't use Google Code, so is that a standard part of Google Code, or is that some additional tooling that was added?
The question is, in the GCR or Google Compute Registry view, the vulnerability pane, is that a new feature, or is that standard part of Google Compute? So that's a new feature that Google Cloud shipped. I'm not sure when. You have to like subscribe to it. They consider it alpha version. The question is, do I know the scanner that they use? I don't know what scanner they use. There's a tool called Snyk that actually has a booth. They have their own tool that does this too. If you want to get more information from them, I'm not sure what GCR uses.
And then the other question I had was, how do you know which Docker image has that vulnerability? So where do you fix it, or like if you are doing the app, like the Java app, how do you know where to fix what should fix?
So the question is, how do you know if there's a vulnerability? How do you know which image to go and fix? Well, yeah. So in this demo, I kind of knew which one. So the scanner would tell you which image might be vulnerable. So in theory, Java could have a vulnerability, Java itself. So if Java itself has a vulnerability, then Alpine Java would have it because it installs the Java APK. So you'd have to know like where you're installing which packages. So kind of automated security scanners that kind of help you with that, because they could alert you when a specific image is vulnerable, and then you can kind of walk back from there and trigger that.
So that's a manual process that you got to do, walk back to the images and then try to figure out which image has that issue, and then the plugin would.
Well, so the automated part of it would be, as I was talking about the intermediate repositories, kicking those off at a time cadence or having a tracker that tracks when a vendor image changes, that would be the best way to do it. So for example, if you're depending on public Java image, then you would have a tracker or a time cadence-based thing that would just pull in the latest version of Java. And then after that, it would kick off the rest of the pull requests to anything that depends on it internally.
So, if I just piggyback on her question, actually. So, one thing I didn't understand was that once you have fixed the vulnerability, actually, right, how do you take it all the way to production? You talk about in terms of how the lift is driving to the production. It means I have a deployed application running in the production right now. You identified a vulnerability, let's say to the pipeline, we fixed it. How do you then take it to the production? Like, what's the process you guys follow?
So the question is, so we've patched all these images, but what takes them to production? What is the path to production process? So there's a number of ways you can do that. So you might have let's say you're deploying your images to Kubernetes. That means you have Kubernetes pod YAMLs with your image name and version supplied somewhere. This was a wish list item, but you can send pull requests to those, and then you trigger those to happen, and then your Kubernetes pod YAMLs get shipped out and rolled out to Kubernetes. Generally at Lyft, once something gets into master, so once you merge those pull requests, you then trigger deployments via kind of a push button process. So anything that made it to master then is expected to roll out. I personally prefer that to be completely automated through pull requests. So if I were starting things from scratch, I would have a repository that has, this is the versions that I have in production, and then pull requests would flow into it. You'd merge it to master, and as soon as you merge it to master, that rolls the train out to production.
But do you have any tool you guys are using which basically tracks whether the vulnerability has been remediated in the production itself? Like this tool provides the capabilities to do the remediation in the image side, but how do you know that it has actually been deployed in production? Do you any dashboard you guys use it to do that?
Yes, I haven't been at Lyft long enough to know, but generally what I've seen is you do security scanning of your production systems out of band. Usually, if you're big enough, you probably have a security team that does that.
Yeah, we use Qualys, for example, as a way to do that. So have you done any integration between does Qualys come back, or I'm just giving an example, does the tool come back and says that the vulnerability has been remediated? I'm just trying to understand, bring the two together.
Yeah, I personally haven't automated anything like that.
Awesome, thank you.
Back there.
What exactly is the linkage? How are you building the dependency chain between the parent container and the children containers? When you showed the repository, it wasn't evident to me exactly how that works.
So the question is, how does the linkage between child and parent images, how does that work? So it just takes advantage of reading the from declaration in Docker files. So in this case, the Falco Alpine image is in from, so we know that the parent image of Alpine Java is this, and that just happens to be the image that we're publishing over here. So it'll read through and search GitHub itself to find everything that has Alpine Java in from.
So when you push to the repository, then it scans all the repos looking for that. You're not storing that dependency graph anywhere?
We are a little bit. So that's the image tag store. But we're storing. You can almost kind of walk through this store JSON to accomplish that, but it'll contain your intended state of what you want the image name and versions to be.
But this just tells you if you scan GitHub and you find an image that depends on
Yeah.
Okay. Cool. Thanks.
All right, going once, going twice. Thank you all for listening and being a great audience. Thank you.